welcome to this video on Cambridge International Examinations. This is the past paper. This paper is the May-June 2014 paper, and the code is 9701/23. So if you're interested, then you can have a go at this paper first, and then you can go through the answers. Go through this video to find out the answers. So this is paper 2. This is the AS paper. This is AS core. Like I say, the whole point of this paper and this video, should I say, is to go through the paper and not only obviously tell you the answer, but also explain what the answer is. Because we know if you look at mark schemes, the mark schemes will tell you the answers, but they obviously won't tell you why it's the answer or explain why it is. So that's the whole point of this video. And if you can see on the top left-hand corner, there are some links, which means you can skip to different questions, so you don't have to watch the whole video. If you just want to look at question 3, for example, you can just click on the link there for question 3. So right, let's just make a start. Let's crack on. Right, so this is question 1, and it says define the term mole. This is the thing that you really do need to know for chemistry. It's the universal unit for chemistry, and so basically it is this. So it is the amount of substance containing, and it's 6.02 times by 10 to the 23 particles. This is something called Avogadro's number. Basically said there's this many particles in 1 mole of any substance, so of that substance. So really, this is something that you do need to know, and that obviously just gets the 1 mark, which is pretty straightforward. Okay, right, so on to the next bit. So it says 10 centimeters cubed of a gaseous hydrocarbon, CXHY, was reacted with 100 centimeters cubed of oxygen gas, NXS. So the final volume of gas mixture was 95 centimeters cubed. So what that means is that 5 centimeters cubed of oxygen was used, clearly, because it's obviously been reduced by 5 centimeters. Okay, this gaseous mixture was treated with concentrated aqueous sodium hydroxide to absorb the carbon dioxide present, and this reduced the gas volume to 75 centimeters cubed. So another 20 centimeters cubed has been reduced, and this is obviously reacted with the carbon dioxide. So it says all gas volumes are measured at 298 Kelvin and 100 kilopascals. That's standard conditions. Okay, it says write the equation for the reaction between sodium hydroxide and carbon dioxide. Right, so pretty straightforward, really. Sodium hydroxide reacting with carbon dioxide, CO2. This will form, when we react this will form a carbonate. Now, sodium carbonate is Na2CO3. Carbonate's a CO3. It's a 2- charge on the carbonate. Sodium is +1, so we need 2 of these to react with the carbonate. So that's just making sure the charges are balanced. You've got to know, obviously, the formula of these. Plus water. Now this needs to be balanced. So we've got 2 sodiums here, so we need a 2 in front of there, and that should get it balanced. So that's for 1 mark. And then it says calculate the volume of carbon dioxide produced by the combustion of the hydrocarbon. Right, so we had 95 centimeters cubed at the start, and now that's gone down to 75 centimeters cubed because this reacted with the carbon dioxide, or any carbon dioxide that was present. So the volume of carbon dioxide is really simply just 95 centimeters cubed that we had at the start, subtract that away from the 75 centimeters cubed that was left over after the reaction with carbon dioxide, and really that's going to make it a nice simple answer of 20 centimeters cubed. And then it says calculate the volume of oxygen used up in the reaction with the hydrocarbon. Well, the amount of oxygen that was left over effectively was 75 centimeters cubed, because we know that 100 centimeters cubed of oxygen gas was reacted with oxygen gas, but 5 centimeters cubed of this was converted into something else. So that's 5 centimeters cubed that was lost. And then obviously of this volume here, some of that was carbon dioxide, because the ammonia reacted with it, this gaseous mixture, reacted with the sodium hydroxide, and that absorbed the carbon dioxide present. So obviously there was 75 centimeters cubed there. So 20 centimeters cubed of this was carbon dioxide. So that leaves this amount here that's left behind is obviously oxygen that hasn't reacted. So this is going to be excess oxygen. Let's just write this down to make it clear. So excess oxygen is 75 centimeters cubed. So what that means is we have 25 centimeters cubed is used, because remember we started off with 100 centimeters cubed of oxygen gas, and so we're left with 75 centimeters cubed. So effectively 25 centimeters cubed is used. So we're going to put that in there, 25 centimeters cubed. Okay, so that gets you 1 mark as well. Right, so on to the next part. So then it says, use your answers to B part 2 and B part 3 together with the initial volume of hydrocarbon to balance the equation below. Right, so what we're going to do is we're going to try and balance this equation here. Now, one of the ways in which we can do that is purely by trying to obviously balance, see how many hydrogens and oxygens we've got. And we know that we're producing carbon dioxide and we're reacting it with water. Okay, so the first thing we need to do is it says, so you can see that we have, if we just go back to the top here, 10 centimeters cubed of gaseous hydrocarbons. So this is 10 centimeters cubed. So this one would represent 10. Now the amount of oxygen that was used, if I just, so this one would represent 10 here. The amount of oxygen we used was 25 volumes of oxygen. So not all of the oxygen was used. So that's going to be 10, and 25 centimeters cubed of oxygen was used with 10 grams of this. And that produced 20 centimeters cubed of carbon dioxide. So if we had to write that as a ratio, the ratio would be, and divide all the numbers by 10 to get it into the lowest ratio we could. It'll be 1 to 2.5 to 2.0. So I'm just going to write that just literally just underneath there. So we'll put that there. And actually, to try and make this whole number ratio, because it'll help with the balancing, if we double all of these, we should get rid of this 2.5 and get it to a whole number. So if we double that, that'll become 2, that'll become 5, and that will become 4. And this should help us to actually balance this correctly, because we need enough carbons and oxygens for this to work, for this to balance. Right, so let's have a look. So if we drag this up here, and we'll see if this works. It says deduce the values of x, y, and z in the equation in IV. So what we have to do is try and work out the value of x. Now we said x is obviously the number of carbons here. So you can see here that we've got a 2 in front of here. We have 4 carbons being produced. So x must be 2 to make sure that we have 4 there. So we're going to put 2 there. And the next one is y. So y is obviously the number of hydrogens that's on this side. And we'll come back to that actually a little bit later on, because we need to try and work out this one. So we'll come back to that. If we do the z's next, actually, so z is the number of waters. So the number of water is the number of water molecules which are here. Now you can see here that actually we've got 2 times 4. We've got 8 oxygens on this side, and on this side we've got 10 oxygens on this side. So actually the number that needs to go in here to make sure the oxygen's balanced, it has to be a 2 as well. So we're going to put the 2 there. And now we're going to come back onto y, because remember y was the number of hydrogens here. Now we can do that because we now know that number. So we know that we've got a 2 there already, and we have 4 hydrogens here because we know z is 2. So that means that the number of hydrogens here must be 2 as well, because 2 times 2 would give 4, which means we have 2 times 2 gives 4 there. So that one has to be 2 as well. Now, that's quite a tricky question. You know, the ratio, it all balances out as well, and that makes sure that you've got the number of carbons and hydrogen. So try it with this ratio first, but you'd see actually the numbers don't quite add up to give you whole numbers here. These have got to be whole numbers as well. So actually doubling up to this ratio actually makes it add up. So you might need to play around with these two together. Okay, right, so on to the next part. Okay, so this is part C. Let's just quickly drag that down there. There we go. So it says another hydrocarbon W with the formula C4H8 reacts with hydrogen bromide HBr to give 2 products X and Y. X and Y are structural isomers of molecular formula C4H9Br. Right, and it says reaction of X with aqueous alkali produces an alcohol Z, but that has no reaction with acidified dichromate. So we'll come on to that later. So give the structures and names of the compounds W, X, Y, and Z. Right. So we know hydrocarbon W has the formula C4H8. So we know this has got to be an alkene, and this will react with HBr, and it will give two products that are structural isomers. So for that reason, we must have an alkene with the double bond must be somewhere near the end of this, because we're going to form two different types of isomers. So this one is actually going to be 2-methyl propene. So I'm going to draw this molecule out here. So we're going to put CH3, CH3. There's a double bond, and the two hydrogens which go on there. Okay, so there's W. And what we do is we can add HBr and we form two different structural isomers. So what that means is actually we can have the Br on the end here, or we can have the Br in the middle here. So they're the two different types of structural isomer that we can have. So let's draw them out. So we've got X though, but let's focus on X first. So it says it gives two products, X and Y. So when we add HBr to this, we get two products. X and Y are structural isomers of the molecular formula C4H9Br. So it says the reaction of X with aqueous alkali produces alcohol Z that has no reaction with acidified dichromate. Right, so what this means, if we're going to produce an alcohol which is Z, and it has no reaction with acidified dichromate, what this suggests is that this is a tertiary alcohol that's going to be formed. Now, to form the tertiary alcohol, we need to form a molecule, a haloalkane, which is X, that has a bromine that is also tertiary in fashion as well. So actually this one, if we draw that structure out, we actually have the carbon in the middle, there's the Br, and then we have three CH3 groups coming from it. Because remember, it's this molecule here that will react to form an alcohol, and tertiary alcohols can't be oxidized by acidified dichromate. So the haloalkane has got to be in this tertiary format. So there's bromine attached to a carbon, which is attached to three other carbons. So this one is going to be called 2-bromo, 2-methyl propane. There you go. So 2-bromo, and then 2 second carbon, 2-methyl, and then propane for the three carbons going across. And that leads us on to, we'll do Z now. Actually, now we know what that is. So we know that Z has no reaction with acidified dichromate. So effectively, we're reacting this with aqueous alkali, and that swaps for an OH. So let's just draw it out here. So we've got the OH there, CH3, CH3, and the other CH3 there. Okay, so this one is called 2-methyl propan 2-ol. Okay, so that's Z. That's that one there. There you go. You just nudge that up, you can see it. So 2-methyl propan 2-ol. And then we have to come on to Y. Now, I did say that Y are structural isomers of the molecular form of C4H9Br. So another structural isomer for this is actually to move one of these CH3 groups over onto the end then, and put the bromine on the end of this carbon here. So we're going to move the bromine here, put the bromine on the end here, and put a hydrogen there. Okay, so that would give a different structure. So let's just draw this out. So we've got two carbons, bromine on the end. There you go. There's your two hydrogens. There's your hydrogen there. We have a CH3 on the end, and a CH3 there. Okay, so this is a structural isomer, as you can see. So all we've done is effectively we have shifted this. So you've got the two CH3s here. We've effectively moved the bromine onto here, onto the end here. And then the hydrogen from here has gone over here. So this is a structural change. So this one is called 1-bromo 2-methyl propane. There we go. So it's quite a tricky question. Again, you get 1 mark for each. 1, 2, 3, 4. So 4 marks in total. Yeah, so you've got to make sure you know about your tertiary alcohols and your structural formulas as well. Make sure you're actually drawing something that's completely different from each other. That's really important. The naming should help you get there as well. All right, and then on to the last part of this question. It's a big question, 15 marks. It says, when W reacts with hydrogen bromide, more X than Y is produced. And so we need to explain why. So here's, obviously we've got W, which is over here. Let's just drag that down. So there's W there. And what it's saying is that actually we produce more of this compound here than this one here. And the main reason is actually when this reacts, we are left with a carbocation. Now, the carbocation intermediate, let's say if I chop that bromine off, you would have a positive charge in that carbon there. And so this means we've got 3 methyl groups all pushing electrons into that carbon, trying to stabilize it. But if I come down to this one and cover that one up there, you can see actually the carbocation is a primary carbocation, and that is not as stable as the tertiary one over here. So you're going to get more of this because a tertiary carbocation is more stable than a primary one, which is formed here. And we call this the inductive effect. These methyl groups pushing electrons into this carbon in the middle. So let's just write that down. So we're going to put tertiary carbocation is more stable than primary, and this is due to the inductive effect of 3 alkyl groups. Now, some of you may also know this as the Markovnikov addition. So this is where you get obviously a preference in different molecules because of the carbocation intermediates. You get 2 marks for that. So let me just highlight where the marks are. You get 1 mark for saying we have a tertiary carbocation is more stable than the primary that we form here. And also we have this inductive effect as well of the 3 alkyl groups. So if I just draw on the diagram here, so you've got these groups will push electrons into this carbocation, whereas this one only has the 1, and so therefore it's well, this one here, sorry, get rid of that. So this one, obviously this methyl group here is pushing electrons into this carbon, which would have the positive charge on there. But there we go. So yeah, make sure you know that. That's 15 marks for question 1. Right, on to question 2. Okay, so this is question 2. And question 2 starts by saying a sample of a hydrated double salt. So we've got CuNH4x SO42.6H2O was boiled with an excess of sodium hydroxide and ammonia was given off. So as the ammonia produced was absorbed in 40 centimeters cubed of 0.4 moles per dm cubed hydrochloric acid. The resulting solution required 25 centimeters cubed of 0.12 moles per dm cubed sodium hydroxide to neutralize the excess acid. Right, and then it says write down an equation for the reaction between ammonium ions and hydroxide ions. Right, so okay, let's write this down. So ammonium ions is NH4 plus. This is obviously something that you really do need to know about the ammonium ions, which is different from ammonia, which is NH3. And this is going to react with OH minus ions, which is from your base, and we're going to form ammonia, NH3. There it is, plus water. Okay, so this is obviously pretty relatively straightforward equations. There's nothing really to try and work out there. Right, and then it says B part 1. It says calculate the amount in moles of hydrochloric acid in 4 centimeters cubed of 0.4 moles dm cubed of solution. Right, so the number of moles, this is just a mole calculation. So moles is concentration times by volume. So the concentration here is that 0.400 times by the volume, which is 40 centimeters cubed. I'm going to divide that by 1,000, and then we should get our answer. So let's bring in our calculator. Right, so it's going to be 0.400 times that by 40, and that will equal 16. Divide that by 1,000, and that should get you 0.016. So it's going to put that over there. 0.016 moles. There you go. So that gets you 1 mark. And the next one, it says calculate the amount in moles of sodium hydroxide needed to neutralize the excess acid. This will be equal to the amount of hydrochloric acid left in excess. Right, so again, another mole calculation. This time it's looking at sodium hydroxide. So if we go up to here, it says the resultant solution required 25 centimeters cubed of 0.1 moles per dm cubed sodium hydroxide. So again, we take concentration, multiply it by the volume, and divide it by 1,000. So we're just going to put in 0.12 times by 25, divide that by 1,000, and then we stick that into our calculator. Let's bring our calculator back in. This time I think we'll stick it over here so we can see it. Right, so this is going to be 0.12, multiply it by 25, and then divide that number by 1,000. There you go, and it's 3 times 10 to the minus 3. So I'm going to put that there, 3.0 times by 10 to the minus 3. And this is the number of moles. And also this is the amount of hydrochloric acid left in excess. Okay, so that's both. So this is moles of OH minus that's been used. Okay, right. And so then it goes on to the next question. It says calculate the amount in moles of hydrochloric acid that reacted with the ammonia. Right. So what we have to do is we have to work out how much hydrochloric acid is left over. And we said that the amount of hydrochloric acid left in excess is the same as the amount of OH minus that's being used up. So we're going to put that there because we need to know how much is left over. So this excess acid will equal, this equals the amount of OH minus ions which we use there. So effectively that's 3 times by 10 to the minus 3. Okay, and then what we have to do is work out obviously how much acid reacted with the ammonia. So this is how much is left over, and this is how much acid was in the solution, which is this one here. So then all we have to do is take this amount, which is the amount we had at the start, subtract it away from this, which is whatever was left over, and that should tell us how much actually reacted. So it's basically this is what's left over. So the acid that reacted is going to be this, which is the amount we had right at the start, 0.016, minus that away from the amount that's left over, 3 times 10 to the minus 3. And then if we put that into our calculator, so let's bring that in here. So we've got 0.016, and we're going to minus that away from 3 times by 10 to the minus 3. And we should get an answer of 0.013 moles. So let's put that over here. 0.013 moles. Okay, so that's just the excess bit. That's how much acid actually reacted. Right, on to the next part. It says calculate the amount in moles of ammonium ions in the sample of the double salt. Right, so what we need to do is you need to look at the ratio first of ammonium ions to the acid. Now this ratio, the amount of acid to ammonium ions is a 1-to-1 ratio, because the hydrochloric acid will react with every ammonium ion. If I just drag that down there, you can see the ammonium ion here will react in a 1-to-1 ratio. So I'm just going to put that on there. So NH4 plus to H plus ratio is a 1-to-1 ratio. Okay, and so what that means is that we have effectively, because we know the number of moles of H plus is 0.013, this amount of moles will react with the same number of moles of ammonium, because it's a 1-to-1 ratio. So that's going to be 0.013 moles of NH4 plus. There we go. Okay, so on to the next bit. It says the sample contained 0.413 grams of copper. Use this information and your answer to IV, which was your previous one, to calculate the value of X in CuNH4X SO42.6H2O. Right, so what we need to do first, we've got a mass of copper, and we need to work out basically the number of moles of copper. And then what we can do, because we now know the ratio or how many moles of NH4 we've got, we can effectively use another ratio to work out the ratio of copper, which is this here, to ammonia, ammonium, sorry, which is here, and that's got the X value because that's what we need to work out. So if we can work out this ratio here, then that'd be brilliant. But we know the moles of this, but we just need to work out the moles of this. So copper, the amount of copper is effectively, remember this is mass over the atomic mass, or the AR. And so the mass we had was 0.413. And this is going to be divided by the relative atomic mass, which is this here of copper. So if we bring in our periodic table, let's just quickly grab one. Go. Right, so for copper, it's 63.5, as you can see there. So let's put that over there. Right, so that's going to be 63.5. And that's the AR of copper. And this will tell us the number of moles of copper. Remember, if we're going to compare things, we need to work out moles. Moles is really useful for comparing masses and amount of substance for different things. Okay, so this is going to give us quite a long number. This is going to give us, let's try and shorten this. This is 6.5 times by 10 to the 1, 2, 3, minus 3. So this is going to be 6.5 times by 10 to the minus 3. And this is moles. So that tells us how much copper we've got. And we're looking at the copper and ammonium ratio. There's a lot of ratios in this. Right, so effectively the number of moles of copper is 6.5 times by 10 to the minus 3. And that's going to be reacting with the number of moles of ammonium, which we know is 0.013. And then if we obviously then work out this ratio, we divide both sides by the smallest number. So this one, this is going to be the smaller number here. So we divide that by 6.5 times 10 to the minus 3, we get 1. So that's going to be 1. And if we divide this one by 6.5 times 10 to the minus 3, let's just bring it in there. 0.013 divided by 6.5 times by 10 to the minus 3. You should get 2. There you go. So that's a 1 to 2 ratio. And so what that means is that we have 2 molecules of ammonium for every atom of copper. So that means we have X, the value of X is 2. So that's that little number there. Okay, and then on to the final bit. It says calculate the MR of CuNH4X SO4 2.6H2O. Right, it's a huge molecule. Right, so let's make a start. Right, so we've got 63.5, and this is the atomic mass of copper. We're then going to add that to, and we've got 2 lots of nitrogen. Remember, now we know X is 2. So we've got 2 lots of nitrogen, so that's 2 lots of 14. We're going to add that to 8 because we've got 4 hydrogens times 2 is 8. And we're going to add that to, right, we're looking at the sulfate. So I know that sulfur, let's bring this in, sulfur is 32.1, as you can see it there. So we're just going to put in 32, there you go, 0.1, and we're going to add that to 16 plus 16 plus 16 plus 16, because that's 4 lots of oxygen. And then if we put that in there, we should get 96.1, and that's the mass of the sulfate. But we have 2 of them, because we've got the 2 there, so we're going to multiply that by 2. And then we're going to add that to 6 lots of water. Now I know water is 18 because you've got 16 for oxygen and 2 hydrogens. So that's going to be 6 times by 18. And then if we put all of that into our calculator, let's just bring this over here. Right, so that's going to be 63.5 plus 2 times by 14 plus 8 plus 96.1 times by 2 plus 6 times by 18, close the brackets, press the equals, 399.7. So it's a huge molecule. And there we are. And they're all 1 mark, apart from this one here, which I'll just show you how the marks are awarded. So you get 1 mark for working out the number of moles, and then 1 mark for actually working out your ratio there. But all of them are just 1 mark, single marks. So that's 8 marks for question 2. Right, on to question 3. Okay, so this is question 3. Question 3 says nitrogen dioxide, NO2, can enter the atmosphere in a variety of ways. State one natural and one man-made source of atmospheric NO2. Right, so a natural way, one of those common ones is actually lightning. So the amount of energy in this can actually create or bond the oxygen and the nitrogen together. So lightning, or we can say the bacteria in the soil that can also leach out and form nitrogen dioxide. So anything like that. A man-made one, it's things like car engines. The amount of heat in a car engine is enough to actually fuse the nitrogen and the oxygen together. So we'll put car engines. They're a big problem. Been a bit of an issue with these regarding car emissions, and some diesel cars producing higher levels of nitrogen dioxide than what is claimed. So this is actually causing a big problem. It's not very nice to breathe this stuff in. So yeah, one of the biggest contributors is car engines. But it's not just car engines, it's also power stations as well. All right, okay, so we get 1 mark for that. Right, the next one, write an equation to show how NO2 leads to the formation of nitric acid in acid rain. Right, so this is just a standard equation, really. So there's nitrogen dioxide, and this is going to react with, because it's going into the atmosphere to form acid rain, obviously there's moisture in the atmosphere, so we're reacting it with water. And we're going to form 2 types of acid here, HNO3 and HNO2. So we form 2 different types here. Now, to make sure that these balance, you can see we've got 2 nitrogens here. We need a 2 on that side to make sure the whole thing balances. But yeah, this is the reaction that we need to be able to write down. Right, so part 3. Use the equations to illustrate the catalytic role of NO2 in the formation of sulfuric acid in acid rain. Right, sulfur dioxide isn't very good either. And sulfur dioxide is formed actually from sulfur impurities in fuels. And when obviously you heat the fuel, you combust the fuel, it reacts with oxygen, the sulfur reacts with oxygen as well, and it forms this SO2, and this can actually even make it even worse. And SO2 is acidic in its own right as well, so it's really bad. So not good. Right, so let's just write the equation down. So it's sulfur dioxide, and it says how it reacts with nitrogen dioxide. So this is going to catalyze the reaction. Definition of a catalyst is it's never used up. So this is going to be reformed later on. So that's a little bit of a prompt, really. And what happens is the oxygen is giving up to here, and it forms SO3. So effectively, the sulfur dioxide is oxidized, and the nitrogen dioxide is reduced. So we're going to put NO there. And then this has to be reformed back again because it said it was a catalytic role. So we're going to bring this down here for our next reaction. So this is going to be NO. And to get it back to this stage, NO2, we have to react it with oxygen, half O2. We only need 1 oxygen to form it into NO2. And there you go. Hey presto, we have our catalyst back. But we've still got SO3. And it did say we're forming sulfuric acid. So this SO3, which is sulfur trioxide, needs to react with something to form sulfuric acid. And that something is going to be water. Again, this is in the atmosphere, naturally. And this forms H2SO4. And that's your sulfuric acid. You get 3 marks for this. So, it's a decent number of marks. You get 1, obviously, for the first equation, 1 for showing the catalyst being reformed, and 1 showing the production of sulfuric acid. So again, if you read the question carefully, it kind of prompts you, but you've got to remember that catalysts always reformed back again. So you start with NO2, you must finish with NO2. And the last equation is showing the formation of sulfuric acid, because that's what it was asking. Right, and B, nitrogen dioxide, let's just shuffle that off a bit. Nitrogen dioxide exists in equilibrium with nitrogen tetraoxide, or dinitrogen tetraoxide, which is N2O4. So here's our equilibrium reaction. So it's 2 moles of dinitrogen tetroxide, was sealed in a container at 350 Kelvin. After equilibrium had been established, the total pressure was 140 kilopascals, and the mixture of gases contained 1.84 moles of dinitrogen tetroxide. Give the expression for the equilibrium constant Kp for this equilibrium. Right, so this is reasonably straightforward. So we've got products divided by the reactants. So you can see we've got 1 mole here. So this is P, and we're going to put N2O4. Divide that by the partial pressure of NO2. But this whole thing, though, has to be squared because we have 2, where are we? There we are. We have 2 moles of NO2, so we must put the square there. So remember, any number in front of here must be used as a power in the actual expression. So that's your mark there. Okay, and then on to the next one. It then says calculate the number of moles of NO2 present in equilibrium. Right, now, this is the number of moles of NO2. So if we start, we need to look at the number of moles of dinitrogen tetroxide that we actually have, because we've been told about this one here. And we're told we have 2 moles of dinitrogen tetroxide was sealed in a container. But after equilibrium had been established, the total pressure was 140 kilopascals, and the mixture of gases contained 1.84 moles of dinitrogen tetroxide. So we started off with 2 here. So let's just write this down here, N2O4. We started off with 2 at the start, but now it's dropped to 1.84. So this is a reduction of 0.16 moles. Now, if we start with the NO2 started at nothing because it was saying after equilibrium has been established. We started at nothing, but obviously this must have increased by the same number of moles as this decreased. But remember, this is 2 NO2, so effectively the number of moles here of NO2 is going to be 2 times by 0.16 because we have double the amount, and so that's going to give us 0.32, and that is in fact our answer. So this is the number of moles of NO2 present at equilibrium. So remember, the number of moles, if this drops by minus 0.16, this will increase by the same amount, but taking into account the molar ratio. So it increases by 0.16 because we've got 2 moles of NO2 in relation to N2O4. We have to multiply it by 2. So that's really, really important for that one. Okay, so on to the next one. It says calculate the total number of moles of gas present at equilibrium and hence the mole fraction of each gas present at equilibrium. Okay, right, so we're looking at the mole fraction. So the mole fraction, let's start with dinitrogen tetroxide, if I can spit it out. Right, so we're going to look at the mole fraction here. So the mole fraction is going to be the amount of moles that we have at equilibrium. So it's going to be 1.84. Okay, and this is going to be divided by the total number of moles of all the gases put together. So this is going to be 1.84 plus 0.32. So if we add them up, that's the total moles of gases present. So that's going to be 2.16. And that will give us our mole fraction. As you can see, it's just a fraction of gases. So what fraction of the total gases is N2O4? That's all it means. So it sounds pretty scary, but it's not that bad. Okay, so 1.84 divided by 2.16. And this is going to give us 0.85. I think we'll chop that one off. So keep it to 2 decimal places, 0.85. So that's the fraction of N2O4 in the total gases. And then we're looking at the mole fraction of NO2. Okay, so again, the total amount of NO2 is 0.32. We worked that out there. Divide that by the total number of moles of gases in the whole system. So let's bring this back in again. So it's going to be 0.32 divided by 2.16. 0.148, but we're going to round that up, 0.15. Okay, there you go. And so that is our mole fractions. So we know that what proportion of each gas is occupying. So 1 mark there, 1 mark there. So you can see we've got loads more by moles, loads more N2O4 than we do NO2. Right, so those are mole fractions, right? And then let's move on to the next bit. Okay, IV. Right, calculate the partial pressure of each gas present at equilibrium. Right, so the partial pressure is the mole fraction times by 140 because this was the total pressure that we had in kilopascals. So the total pressure was this. So we need to work out the partial pressure of each gas. So this is going to be the partial pressure of N2O4. And that's going to be, now we worked that out as 0.85 because that was our mole fraction, remember? Multiplied by the total pressure, which is 140. And so that's going to give us 0.85 times by 140. That's going to give us 119. 119, and that's in kilopascals. And then we need to do the same with the other one as well. So this is NO2. So the mole fraction of NO2, the fraction of gas is 0.15. Notice these two add up to 100. They've got to add up because obviously that's the only gases that we have present. Multiply it by the actual pressure that this thing was in, and then stick that into the calculator. 0.15, multiply that by 140, 21. Okay, so we're going to put that on there. 21 kilopascals. Right, so we get 2 marks for that. So again, not too bad really. You've got to know these equations though. Obviously, you might be a bit stuck if you didn't, but make sure you know them. And the last one is V, on part 5. Calculate the value of the equilibrium constant Kp at 350 Kelvin. Give your answer to 3 significant figures and include the units. Right, okay, so we're going back to this our original expression, so it brings us back full circle. Here's our Kp expression, remember, so we have the partial pressure of N2O4 divided by the partial pressure of NO2 squared. So we're just going to put them numbers in. So let's put in, so this is Kp. So partial pressure of N2O4 is 119. Divide that by the partial pressure of NO2, which is 21. That's going to be squared. And then we're going to put that in our calculator. 119 divided by, and we're going to do 21 squared. And that gives us 0.269, or if we round that up, that's going to be 0.270. Okay, 0.270. The units, now how we can work this out is obviously with kilopascals on the top, and then kilopascals on the bottom as well. And effectively what we can do is cancel these out, shove this up at the top, so that inverts the sign, so that becomes kPa to the -1. So that's what we're going to put there, kilopascals to the -1. So the answer goes in here, 0.270, and the units are kilopascals to the -1. There you go. So we get 2 marks for this. Obviously you get 1 mark for the answer, and we get 1 mark for the units as well. But there we go, 13 marks. On to the last question. Okay, so this is question 4 and the final one in this paper. So it says the halogens and their compounds have a wide variety of uses, and the chemical and physical properties of the elements show regular patterns related to their positions in group 7. So it says chlorine, bromine, and iodine all react with hydrogen. So state the trend in the reactivities of the halogens with hydrogen. Right, so the reactivities of the halogens as we go down the group, they decrease and they become less reactive. So let's just put that on there. Okay, so we're going to put decreases down the group. Okay, right. And then it says, explain this trend in terms of bond energies. Right, so effectively, as we go down the group, the halogen bond between the 2 halogen atoms decreases. So obviously, if we start from Cl2 going down to I2, but the decrease in strength of the hydrogen halogen bond is a lot more significant. Yeah, so that's why they all do react with hydrogen. So we're just going to write that on there. So we're going to say this halogen bond, the XX bond, strength decreases from Cl2 to I2. but decrease in strength of the hydrogen halide, or the hydrogen halogen group, down the group is more significant. Okay, so we get 2 marks for that. So we get 1 mark for saying that the halogen bond on its own, that strength decreases as we go down the group. But we say, well, actually the hydrogen halide bond, because remember this is reacting with hydrogen, is actually a lot more significant than this. So it's going to have a bigger effect on bond energies. Okay, right, and then part B. It says, in the laboratory, it is not very convenient to prepare hydrogen halides from their elements. Hydrogen halides can be prepared from their salts. It says, write an equation for the reaction of calcium chloride, CaCl2, with concentrated acid. Right, so let's make a dint into this one. So calcium chloride, CaCl2, will react with your sulfuric acid, H2SO4, and this is going to form calcium sulfate. And we're also going to produce HCl. Now we're going to make sure this balances, so we're going to put a 2 in front of there because we've got the 2 chlorines there. Okay, so that's pretty straightforward. And then part 2 says, explain why hydrogen iodide is not prepared in this way. Well, actually, iodide ions, I-, are very good reducing agents, and what they do is they reduce the sulfuric acid, and as a result, iodine is actually made, so I2. So it's not really a good idea to use that for that reason. So we're just going to put that on there. So I- ions reduces H2SO4, and we can say that iodine is made. Okay, so that's part 2. Right, and then part 3. When potassium bromide, KBr, reacts with concentrated sulfuric acid, sulfur dioxide, SO2, is produced. State what you would see and write an equation for this reaction. So we're producing SO2, so what we'd see is some kind of like brown. Well, we've got the bromide here, so this will produce bromine, so you get this brown gas produced. Or you can say SO2 is, you get these fumes being produced as well. You can't really see SO2 though, so you get fumes produced as well. So that's what you'd see with the brown gas because of this bromine vaporizing. Right, and the reaction that we're producing, right, we're going to split this up. I think it's easier to write an ionic equation showing what's happening. So we've got H2SO4, and this is going to form sulfur dioxide because we've been told that. Now, if we're going to balance this, we should use the water, proton, and electron notation. So you can see here that we've got 4 oxygens here and only 2 oxygens here. So we're going to react that. Obviously, we need waters over here to balance out the oxygens. So we need 2 waters here. And we use water to balance out oxygens. You can see here we've got now 4 oxygens on this side and 4 oxygens here. Don't worry about the hydrogen here yet. Okay. Then we need to balance hydrogens with protons. So you can see on this side we've got 4 hydrogens on this side and only 2 on this side. So what we need on this side is 2 more hydrogens. So we're going to put 2 H+. Okay, so we're balanced with the H+. And then we use electrons to balance charges. You can see it's neutral on this side, 2 plus on this side. So we need to have 2 electrons on the left-hand side there. Okay, and the other one, it says, because we've got 2 half equations, so we've got KBr. So I'm just going to put Br minus, which is there, and that's obviously going to form Br2. So we'll need 2 of them to form this Br2. And electrons, we're going to put electrons over here, because you can see that's 2 negative, that's neutral. So we need to put 2 electrons over on this side. And then all we do is we then cancel out these electrons here, and then we rewrite our fully ionic equation. So literally it's going to be H2SO4, and that's going to react with 2H+, and that's going to react with 2Br minus. So everything on the left-hand side of these equations is written here, and that's going to form SO2, sulfur dioxide, plus Br2, which is there, plus 2H2O. And I think that's probably the easiest way of writing these equations, because otherwise it ends up you trying to remember a very long equation. So we've just combined, written two half equations, combined them, and written our full ionic equation. Okay, right, so we get 3 marks for this. So obviously we get 1 mark for talking about our misty fumes being produced, or brown gas, and you actually get 2 marks for writing a correct equation. So we'll put that there, and you could write the 2 half equations. You could get the marks there as well. Okay, so 3 marks in total there, not too bad. Right, on to the next part. Let's put that away. Okay, so C part 1, it says give the structure of the 4 structural isomers of C4H9Br and identify each as primary, secondary, or tertiary. Right, so structural isomers, we need to think about how these are structures. The first thing I think we should do is just write down these straightforward 4 carbons in a chain, 1, 2, 3, 4, with your bromine on the end. I think that's probably the easiest one to write down first. So let's just add our hydrogens on there. Okay, right, so this one is going to be primary. Okay, we could have it where this bromine's in the second carbon. So add our 3 hydrogens on the end, hydrogen there, Br there, hydrogen, hydrogen, all the hydrogens. Okay, and this is secondary. Okay, right, then we need to start and be a little bit more creative. So we need to now start and change the structure of these carbons here. So we could have something like this. Right, we're going to put CH3 up there, CH3 there, and then a H. Okay, this one again is primary. The bromine is bonded to 1 carbon only, so that's going to be primary. And that carbon's only bonded to 1 of the carbons as well, so that's what makes it primary. Or we can have this one, where we can really go the whole way and just surround this carbon with loads of CH3s. So this one, this bromine is bonded to a carbon, which is bonded to 3 other carbons, so that makes it tertiary. Okay, so we get 4 marks for that. You get 1 mark for each one. So let's just quickly sketch them in. So get 1 here, 1 here, 1 here, and 1 here. There you go. So that's pretty easy. Right, section 2. Part 2, should I say. Right, so it says name the isomer of C4H9Br that contains a chiral center and draw the 3-dimensional structures of the 2 optical isomers. Right, so a chiral center is something where we've got a carbon with 4 different groups around it. So we need to look at our different structures here. So if we look at these different ones, we're looking for one with 4 different groups, and we can see here straight away that this is our chiral center. We've got a bromine here, we've got a hydrogen here, so that's 2 different groups, a CH3 group to the right, and a C2H5 group to the left. So this carbon has got 4 different groups around it. So this is the one that's going to be chiral. Now the name of this is 2-bromobutane. So that's the name, and that's what we're going to put in there. So the name is 2-bromobutane. Okay, and the structure, carbon, CH3 on there, C2H5, Br, and then your H. And its mirror image is literally going to be the same. Carbon, CH3, dotted line, C2H5, which is going to go there, Br, and then hydrogen. Go. Right, so we get 3 marks for this. Again, quite a few marks. 1 mark for obviously naming it properly, 1 mark for drawing that molecule, and 1 mark for its mirror image as well. So we get 3 marks in total there. Right, okay, and then on to the next one. Let's just nudge that down there. Right, so it says aqueous silver nitrate solution was added to separate tubes containing chloroethane, bromoethane, and iodoethane. The tubes were heated in a water bath. A yellow precipitate appeared first in the tube containing iodoethane, followed by a cream precipitate in the tube containing bromoethane, and finally a white precipitate appeared in the tube containing chloroethane. Explain these observations. Right, so what we need to say is effectively the halide ions are effectively being removed from the alkane, and that's going to react with the silver ions. What this means is that effectively we're going to form this precipitate. But the most important thing is that actually the iodide ones are actually going to turn first, because that's the weakest bond. The CI bond is the weakest one, followed by the CBr and then the CCl, which is the strongest bond between them. So because it's a stronger bond, it's going to take longer for that halogen to effectively drop off and react with the silver ion. So let's write this down in words. So we've got halide ions. So the halide ions are released, and they form a precipitate with the Ag+, that's your silver ion, and obviously the rate at which these things are actually changing colour is due to the decreasing bond strength. So we would have CI, CBr, and I think we're just going to run a space there, CCl. So as we go down this group here, this bond is actually becoming stronger. So you've got a stronger bond. And so that's why this one takes longer to change colour compared to the CI, which is the one at the top. So you get 2 marks for that. So you get 1 mark for saying the hydrogen halide is released to form precipitate with Ag+, and you get 1 mark for that one there. So you get 2 marks in total. Okay, right, on to the next part. Okay, so this is, let's just drag that down there. Right, so this is E part 1. So it's give the full name of the mechanism for the reaction between aqueous sodium hydroxide and bromoethane. Right, so effectively what we have is the hydroxide is a nucleophile because it's going to go for a delta positive carbon. And because the bromine is being swapped with an OH, this is substitution. So we call it nucleophilic substitution. Okay, so you get 2 marks for that. Obviously, 1 for saying nucleophilic, 1 for saying substitution. Okay, and the next bit says complete the diagram below to represent this mechanism. Include all necessary curly arrows, partial charges, and lone pairs. Right. So we're going to put a lone pair on the oxygen. We have a partial charge here. This bromine is delta negative, so it's going to draw electrons towards itself and leave this carbon delta positive. And these lone pairs here are the electrons are going to go, the arrow is going to go from the electrons to the delta positive carbon. And this is effectively starting to form a bond with this carbon. So this is going to have 1, 2, 3, 4, 5 bonds. That's far too many. So carbon has to get rid of 1 bond or break 1 bond. So this bond is going to be broken here because this is the weakest one out of the lot. The electrons from this bond are going to move onto the bromine. And so that is our mechanism there. And we get 2 marks for that. We get 1 mark, obviously, for, let's just label that up as 1 mark and 1 mark. Get 1 mark for this arrow and then 1 mark for that. But your lone pair and your partial charges must be present, otherwise you don't get the mark. So that's very, very important. Okay. And F. Okay, so let's just notice that up there. Okay, so F. It says, in the past, CFCs such as CF3Cl were widely used as refrigerants. State a property of CFCs which makes them suitable for use as refrigerants. One of the main reasons why they use this is because CFCs are actually inert, so they didn't react with anything, and they're quite volatile, so they could absorb heat quite well as well. So we're going to put inert because that's the main reason why they were used, and that actually leads to their fault as well. So because actually when they go up into the atmosphere, they don't react with anything in the atmosphere, and so therefore they rise up into the atmosphere and they cause this problem here, which we're going to explain here. So state the damaging effect of CFCs in the upper atmosphere, and what they do is they destroy the ozone layer, which is no good at all. All right. We're going to explain our answer as well. What happens is the CCl bond here is broken by UV in the upper atmosphere. And effectively you form free radicals. And this obviously leads to a chain reaction which breaks down ozone. So yeah, let's put that down there. So the CCl bond is broken by UV, and we can say that free radicals are produced. Okay, so this whole thing's out of 2, so we get 2 marks for this. So we get 1 for saying that they destroy the ozone layer, and then 1 for obviously explaining your answer of how they actually do that. So there we go. That was a big question, 24 marks. But that's the end of the paper. I hope you've done reasonably well in it. Make sure that you are checking your answers. You are putting all these keywords in there, and you should come out with your top grade of an A. That's it. Bye bye.